Okay, so I was gonna do this crazy little project in steps and be like, okay, here's your RCWL 0516 with an LED. Now here's it with this and that and this and that. And you know what? I decided that I didn't want to go through all that BS. So I've jumped you into the far future with these boards. Now you can see there's a wire soldered to it. What I have done here, I'm going to give you a full entire breakdown of what this is, how it works, and if I can get the thing to stop spinning on me. Okay, check it out. So, what you have is the RCWL, I hope I've got that right, 0516 radar module board, super cheap on Amazon. This one uses the RCWL 0001 chip, not the 9169 you're probably all familiar with, so it's a different board design. You can't just go on the internet and look this up and apply what you see on the reverse engineering sites to this, because you'll fail miserably every time. What I did is I soldered a wire to pin 12. I could not understand why it didn't line up with what I was finding on the internet, because it doesn't line up with any of that. Pin number 12 goes to nothing. It is zero connection, no connection to anything. I know because I scraped one of the chips off of one of the boards, and it just goes nowhere. It's not connected. Same with pin 13 right above it. But nevertheless, it works like they say on the internet, and pin 12 does give you the analog out. So what it's giving you is the direct signal that it uses in order to establish whether or not it should trigger. So I soldered a wire to that pin. I led that out to a 22 kilo ohm resistor and that big fat green non-polar 10 microfarad capacitor. That goes into pin number 2 of a 1641 OPA 1641 op-amp chip. I chose that not because it's amazing, which it is, because it was there and it wasn't being used in a project, and it turned out to be a really great choice. It's great for it. On that op-amp, I have this variable resistor that is, as far as I know, 1 kilo ohm. That adjusts the bias on pin 3. Feedback on the chip is a 0.0001 microfarad capacitor. I'm obsessed with microfarads. Otherwise known as 1000 picofarad or picofarad, whatever, or 1 nanofarad. And a 470 kilo ohm feedback resistor. That then goes out to this gigantic honkin' 470 microfarad capacitor, which delivers the output. That right there is your power. That is a 7809 regulator, just linear regulator, 9 volt. So this is delivering a more or less centered waveform at 4.5 volt up and down. Now these do not put out a balanced waveform at all from pin 12. It is very heavily biased low, and so this whole setup was designed to deliver something reasonably balanced out of something that really, really isn't. But it does work very, very well. So what you do, you throw all this together. Don't connect the radar board right to the chip just yet, but do all the rest for the op-amp. Set your bias at midpoint, and with a voltmeter on the output of the chip, directly on the output of the chip, not through the cap, obviously. And center it up, then connect the radar board through that capacitor and resistor into the chip, and it will remain nice and balanced and centered. And then your output is giving you the AC waveform equivalent of that, biased DC voltage, etc. Now moving on over to the results of this. That then goes to this. This is a Raspberry Pi 4B. I have 4 gigabit RAM edition, I believe. And if, it's very old, so if my memory serves, that's what it is. Gigabyte, excuse me. This here is your typical MCP 3008 setup, but I'm not using the 3008 chip. I'm using the 3304, which yields 4 times the resolution at the same wiring and the same speed and the same voltage requirements, same everything, same company. It's just a far superior chip. There are some slight changes in sampling that I will cover later, but for all intents and purposes, that's what it is. Now, this is the cable running out of the radar setup, the radar module setup, and I have it's just going through a variable resistor so I can adjust the maximum level of the signal. It's just a simple divider with the 2 ends, the fixed resistor ends going across the output of the module, and then the arm, the wiper of the pot is going into the sampling on the chip. And I have a 100 microfarad capacitor across that to reduce the noise a little bit, and I'll show you why in a second. The magic of time travel, that second went faster than it should have, but that's cool. So this is why the variable resistor on the sampler is because, it's spitting out more than the ADC chip would like to have if you just run it through, because I got 9 volts on the module and the op amp. So it's capable of delivering 4.5 volts, which is over the 3.3 it would like. So I can adjust it down so that the peaks are just hitting 3.3 volt. And there's the result. This particular grapher program, this is running locally on my PC. I have the Raspberry Pi 4B send its data down a socket setup in Python, and then the PC picks it up and processes the data into this graph. The 4B will run these graphs just fine too. In fact, I have it running Matplotlib 24/7 in a much lower, much lower frame rate setup. It only updates once a minute. This is yoinking down about 20 on a good day, 20 frames per second. But yeah, Pi 3B or Pi 4B will run Pi QT, whatever it is, just fine, just not as spiffy fast as a modern PC will do. Anyway, I'm babbling. There's the graph, and you can see if I hold very, very still, the noise floor will fall to about 0.5 volt up or down by a little bit. If I move even the slightest with that module, aiming at the ceiling in that shielded box, it will still max out. Now here's what's really interesting. If I then turn it around and pin it against the wall between these two places, it will pick up people on the other side. It's not amazing, but if they get close enough to that wall, it will max it out. And if they stay middle of the room on the far side, it will deflect quite strongly, like about similar to what you see here. So you can use this to monitor an entire room with ease just by aiming it up at the ceiling, and in fact it will get me in the other rooms, even though it's in this room in the far corner. It works surprisingly well, and this kind of setup does really, really well as an intrusion alarm. I could have it monitor the signal and act based on a certain amount of deflection of the signal for a certain duration, and then send me alerts easily. or I can just use it to monitor regular traffic and look at the matplotlib version of the graph, which is running concurrently on this Pi4B as we speak. It's not only delivering this data to the PC, but it's also graphing matplotlib all the time. The graph's a rolling graph, so the oldest data, 25 hours old, rolls right on out. The new data rolls in and covers it up, and that never, ever, ever stops. So I can look back at that and I can say, oh, somebody was moving here at this time. Somebody was moving there at that time. I got up and moved around in the house, although I don't remember it, in the middle of the night, etc. These are really great for like controlled environment intrusion alarms or traffic alarms. Pretty interesting. But yeah, so there you go. There's a breakdown of that. Oh, wait, I want to give you the circuit really quick because I know people are going to ask. Okay, so here is the module circuit setup. I'm not going to waste time giving you the ADC setup. You can go fiddle around with that on your own. This basic toy right here, you can actually listen to it. You can plug a headphone into it and listen to the device, and it is surprisingly audio frequency. It sounds just like a radio receiver. It's kind of fascinating. These are the reasons why you use analog instead of digital on these stupid frickin' 2-second timer modules, because you can actually listen to the interference and the deflection in real time with a headset. It's pretty fascinating. Anyway, as you can see, this is the module. That little squiggle was supposed to be the lines on the board. Anyway, pin out. On pin 12 of the IC, you have to wire to the chip directly because, as I said, it's no connection. Soldered to the board on a pad, but the pad goes nowhere. So you have, what I did is I dropped straight down in and then bent the wire over the top of the chip after soldering it, and then crazy glued it in place to make sure it wasn't going to wander. That feeds out through a 22 kilo ohm resistor and 10 microfarad non-polarized cap in a series pair. You could probably easily use less capacitance. It's what I had, and it was non-polarized, and it did a nice job, so I went with it. That goes into pin, I didn't label the pins, I'm sorry. That goes into pin 2 of the chip, the OPA1641 chip. On pin 3, meanwhile, it's just a simple variable resistor. The wiper goes to pin 3, the other two pins go to ground and VCC, 9 volts DC respectively. Meanwhile, on pin 2 here and pin 6, you have a 470 kilo ohm resistor and a 0.001 microfarad or 1 nanofarad or 1000 picofarad cap. And what this does is it just gives you really, really good gain to recover from the 22 kilo ohm, watering it way down, and meanwhile that rather large capacitor slows down the acquisition and rules out some noise because they are very noisy chips. The radar module I meant, not the OPA1641. It's a very good chip. Nice rail-to-rail audio class chip. And then here you got, 470 microfarad going out to whatever you want to do with it. You could eliminate that and just, study the DC. You could short this out, but keep that 22 kilo ohm there. Anything less, and it just dies. It's very sensitive to load, so you have to have a large resistance connecting pin 12 to whatever you're going to do with it. That's why that big 470K resistor, it's a lot of gain. because you have to have a high resistance. Sorry, I'm shaking. You have to have a very high resistance connecting the module on pin 12 to the rest of the circuit, or it just simply will fail. You can go up if you want, but it just gets more and more ridiculous with adding gain to make up. So I found that to be a decent compromise. 10 kilo ohm might work. I stopped. I was tired. I was tired of playing with it. But yeah, there's your circuit. And easy peasy. And you can do a lot with this, like an awful lot. Limited only by your imagination, and if you still want digital triggering, then process your signal into something useful. Or just suffer with 2 seconds worth of on-off for every stupid thing that comes along. Personally, I find this much more appealing. Anyway, there you go. Hope I didn't leave anything out. If you want, go ahead and ask me stuff about the ADC and I'll help you there, because the MCP3304 ADC chip does require just a little bit different data processing when being sampled in Python. Other than that, have a great day. Hope this was useful for you, and see you next time. Thanks for watching.